Thank you very much, Rosman, for the nice presentation. Thank you, everybody. It's the last, almost the last day of the term, so it's good. We are all happy, I guess. And I don't have to make jokes because it's the revision classes and I had to get the good evaluations, I guess. But I mean, we are all happy that the term is finishing. Good. So, okay. So today I would like to talk about these repulsive attractive models in collective behavior. Is a theme in which I've been working already for more than 10 years. But today I want to discuss a particular issue related to the case in which you have more than one species. So most of my talk is going to be related to that. And let me start by showing you two experiments that somehow triggered my attention to this particular problem, okay? So this one is an experiment that was conducted in Japan by Hideru Togashi. He's a biologist. Hideki Murakawa is a mathematician. And they wanted to understand the behavior of cells with different protein level that affects the way in which the cells, they're able to have an interaction with others, in the sense that it controls the adhesive force between the cells. So that's why you had the green and the red. Both of them are just the same type of cell, just expressing different level of a certain this nectin EGFP protein that affects the adhesive force between them. So the adhesive force between the two types of cells is just different. And then depending on that, well, in the first case, they are the same type, if you want, almost. So they don't intermingle. While when you change the way in which the two interact, then there is a kind of mixing region where both of the species, you can find them in with certain density. Okay, so I will come back to that later on. The other one that triggered my attention is this pattern formation in zebrafish. So there are 2 or 3 groups in the world that are working quite heavily on this problem. On one hand, the one of Nuslein Volar, which is a Nobel Prize in biology, Shigeru Kondo in Osaka, which is the one that we have more interaction, and there is another group that I don't have listed here in the US. Essentially, what they are trying to understand is the formation of these patterns, stripe patterns on the zebrafish. That is related to the interaction of mainly 3 types of cells. I will come back to that later, but at least there are 2 of the cells that are given the yellow and the kind of dark color. And, well, they have some assumptions about, and they know certain behavior of the cells, that the interaction between themselves, and they want to explain why they produce the formation of that kind of pattern. So, as I said, I will come back to that later. Okay, so what's the kind of modeling that I like to think in general about these problems? So I show it to you by showing you some pictures of my home institution. So somehow we want to go from some kind of macroscopic model in which we really care about explaining the behavior of the individuals that form the group, to something that is going to be much more macroscopic, like the whole area around Imperial College and the density of individuals that you can find over there. But mainly, many times, what we would like to do is to somehow bridge these 2 descriptions by some kind of middle ground. So, morally speaking, it's like 3 levels of description of the same system, and you have mathematical ways of bridging the different scales of the system. So, typically at microscopic level, you are talking about individual-based models. At the macroscopic level, you talk about population-based models, and typically one way of doing it, and the way in which I typically think about this problem, to bridge these 2, I use kinetic tools in order to bridge one model into the other. So today I will not talk that much about this level, and mostly I will discuss about this level, but I will derive that directly from the macroscopic level, okay? So let me start with the basic brick in this story I want to tell you today, which is about the related to the aggregation diffusion equation and how to derive it from macroscopic description. So let's do a very simple a model based on m particles. You have m particles that you are assuming that they are interacting with a certain force. The force I'm going to assume that is derived from a potential that I call W. So the force that the presence of the individual I is producing on the J, or vice versa, is just given by a force directed to through the center, say, of the two individuals, Xi and Xj, and derived from that particular potential, as I mentioned. So here you have kind of a typical shape of a potential that I'm gonna discuss, so attractive, repulsive, meaning that if the particles are very close to each other, they would like to separate from each other. And this I can see from the signs that I impose in the equation by saying the potential is decreasing as a function of the radius. This means that it's repulsive, while if it's increasing, it's attractive. Okay, so essentially you have a repulsive near the origin, attractive for long distances potential. What you are defining is a kind of typical length scale of interaction. Okay? Good. So associated to that particle system, you're going to write a rule about how the particles interact. In this way, my rule is just to assume that the velocity field of each of the particles will adapt instantaneously to the sum of the forces, so there is no inertia term. Or if you want, you can put it there, but then assuming the inertia term is negligible, okay? So then I have x dot equals the sum of all the forces, so I sum the gradient W xi minus xa, and this is important, I have a 1 over n in front. Why I do have the 1 over n in front? Because I would like to have later on a kind of macroscopic model in which I have infinitely many of these agents and I want to track macroscopic density. So then I need to scale the total force in such a way that when n is large, still the total force is of order 1. Okay, this is what is called the mean field scaling. So that's why I'm dividing by 1 over n. Well, associated to that, in order to derive the kind of macroscopic description, what you can do is to define the empirical measure associated to the dynamical system. This means that you know exactly the position of each of the individuals. So then with probability 1, they are going to be at probability 1 over n, they are going to be at a certain xi of t. Probability 0, they are outside. So then it's a sum of Dirac deltas at the locations of the particles. Good. Formally, you can write then what's the equation satisfied by mu n of t. That's an exercise of a graduate course in weak solutions of PDEs. Okay, you can check that this is a weak solution of that equation. So somehow is the way in which you recover that maybe when n goes to infinity, you expect that that is going to be the kind of macroscopic model. So, and it's quite intuitive, no? Because what you are writing here is a kind of continuity equation of a certain density that I'm denoting by mu. And the velocity field is given by minus the gradient of the potential composed with mu, that we can think that is like the continuous version of that sum of all the forces. Okay, so it's essentially the same idea. I'm summing all the forces. Now I have infinitesimal parts of the measure, maybe. So each of them, they are producing a force onto the others, proportional to the mass and in the direction of the gradient of W, and then I add all of them. Okay, good. So in this way, you compute the velocity of each of the individuals, and the weights are depending on the distance, just as I said, because of the potential W. Good. So the interesting thing about that, and you will see that later on in my talk, is that they can lead to interesting stationary states or even some other patterns, as you will see, just by choosing relatively simple potentials. Okay, let's come back for a second to the application I was explaining at the beginning, or the two kind of applications, both of them were involved in certain type of cells that were interacting. So let's try to make a more sophisticated model about those kind of two type of cells. Okay, so in principle, I'm going to assume that the cells, they have some typical body diameter, and that I can compress them, but I cannot compress them too much. I mean, the worst I can do is to compress them up to, for instance, the radius of the nuclei of the cells. Okay? So how can I model that? So we can model it by saying that if they try to get the center, say, of the cells, they try to be too close, closer than whatever is the distance that you define, then there will be a strong repulsion to separate. This is a way of modeling a volume exclusion. On the other hand, one thing that was very well described by the biologists is that many of these cells, they produce very long philopodia, and the way in which they interact is that when they touch, they immediately either they like to continue get attached to the other cell, they like them and they kind of pursue the other cell, or they separate. So there's a kind of attraction repulsion depending on the type of cell. Okay? But that you can model through some kind of more non-local force. So it happens at a certain distance. Yeah, I should have shown here a movie that's from the webpage of Kondo, but I didn't have the time to look for it. Well, if you're interested in it, I can send you the link. Anyhow, so the typical potential that you could think of is something that is very repulsive up to a certain distance, then some adhesive property, and typically after a certain distance, there is no interaction. Okay? That would be a typical potential that you could think in a very simplistic way about the interaction of these two types of cells. And if I have red and blue, let's say that I can define, depending on the interaction between the cells, different potentials for each of them. Okay, so I can have different potentials between the interaction of the blue with the red, or red with the blue if the red likes the blue, or the blue doesn't like the red, for instance. Okay? Good. So if I continue with the kind of modeling perspective I was doing before, so one could say, okay, let's write first order model with two type of particles, these four kind of potentials, different number of particles, and then I can try to write what is the mean field limit of this, say that when I send n and m going to infinity, what is the corresponding system of PDEs that we'll have for the densities of each of the two species. Okay, now it's not surprise now, based on what I said before, that I would expect to have such a thing in this particular case. Okay? Well, you can prove that, depending on the potentials, rigorously if you want, but you expect that this could be a good continuum version of that particular system. So again, you have two continuity equations for each of the two densities, but now you have a velocity field that depends on their own density and the other, with different interactions possibly. Okay? Good. So when I write mu1 and mu2, it's because I was thinking in them like probability measures. That's how I pass to the limit and so on. But sometimes when you are at the continuum level, most likely, and depending on the potential you have, maybe it doesn't make sense to even do it with probability measures. So I'm gonna write things, when I write rho and eta, like now I'm having here, I do that just to say that instead of measures, I'm thinking about nice functions. Okay? Think about it as an L1 function at least. Okay? Good. But on top, I'm going to do the following approximation. I said before that in most of these systems, you have clearly one constraint, which is that you cannot compress the particles too much. So there has to be a very strong repulsion to compression if you are pretty close between the two particles. How I introduce that in the model? So in fact, I introduce it by assuming that part of the potential is a very strong repulsion at the origin. So in fact, if you want, It's like saying for each of these potentials, I'm going to extract part of it. So I'm defining W as W tilde plus the Dirac, and then I get rid of the Dirac, of the delta, of the tildes here. But if I do that, I'm just saying that there is a very strong repulsion concentrated at the origin. So I have this strength of the Dirac at 0, that if I put it formally here, so just put it in one of those terms. If I put a Dirac here, so what I get is the gradient of the corresponding function multiplied by 8. So that's why I have these 4 terms over here. Okay? So I have a part now that I'm separating, which is this strong repulsion at the origin, that depends on the total, that now is proportional to the gradient of the total population. So for those of you that know a little bit about this, so forget about all of these potentials here. If you add the 2 equations and you keep your concentration only on those terms, what you get is what is called the porous medium equation for rho plus eta with exponent 2. So in fact, somehow what I'm using is the fact that the strong repulsion concentrated at 0 for the non-local term, it can be understood as a local repulsion, and then this becomes a kind of nonlinear diffusion term, because I will have, in that case, for the total population, Laplace of rho plus eta square. Good. So let's even ask ourselves now, okay, what can I say about particular solutions of this problem? Okay, so then, as usual, we are applied mathematicians, so we go to cases in which we can do some computation and we can find some properties of particular solutions to get a grasp of what we can expect for the whole model. Good, so let's do that. Let's go to one dimension and let's see how complicated the model is. So I'm going to do one dimension, I'm going to choose the potentials too in the simplest way. So I'm going to concentrate myself on 2 cases. One that I call attractive, in the sense that both type of cells say they like each other. It's like the first experiment I showed you. The green and the red, both of them, they like each other, but with different strength. Okay? One like the other more than vice versa. Okay? So the reds, they like themselves more than the red with the green, and maybe the greens between themselves, they like them less than with the red, and these kind of things. Okay. So, but also you can think about the attractive repulsive in the case in which the red likes the green, but the green doesn't like the red. Okay, which is the case more or less of the zebrafish patterning that I will come back later. Good. Let's choose potentials. Okay, so surprise, I'm going to choose the potentials in which I can do more computations explicitly. So for the self-interaction, I'm going to assume that they like each other, and they like each other very strongly with a potential which is very, very attractive, x squared. Okay? Good. For the cross-interaction, either if it's attractive, repulsive, or attractive, I'm going to assume that they like or they dislike each other like modulus of x, with the potential modulus of x. Why modulus of x? Rasman knows perfectly, because modulus of x is the fundamental solution of the Newtonian in one dimension. Okay, so then one can do plenty of computations here. Good. So the thing is that in that particular case, if you look for steady states for the system, the steady state should satisfy that property. Well, this is not too difficult to see, because I just come back here. You see if the whole velocity field is 0 on the support of rho, and here for the second, the whole velocity field of the second species is 0 on the support of eta, then you will have that is a steady state. So for the, remember the velocity field was the derivative of that quantity, so that quantity is a constant. Okay, so if you do some algebra, you can realize that you can solve this explicitly, even if it looks so complicated. So you can see that, for instance, when one of the species is 0, but the other one is not, then you can solve it explicitly and they become just pieces of parabola. But if both of them are non-zero, then you can see that it's a bit more complicated, but it's still explicit, This is a combination of sine and cosines, where the M1 and M2 are the total masses of each of the two species. Okay? The interesting thing is that you can check explicitly that things like that are steady states. So let me explain what you have here. You have the two species, rho is the blue, eta is the red, and then what you have is that there is a sharp transition on the support of each of the two species. So you see here, it's the case of attractive, so you have one species on top of the other, in a sense. But then you have this sharp interface at the boundary of the support of the eta. So this, for obvious reason, we call these kind of steady solutions Batman profiles. Okay? So we have our Batman profile here. And in fact, the Batman can get a bit more complicated. You can have a little piece of the support of one of the densities outside the one that was in the center. But again, you have the same business, that you have a sharp interface between the supports of the two. So here there is no a kind of segregation, but you have that, you have the consistency between the two species, at least in part of the support. Yeah?
What's the difference between the two figures here?
It's just the value of epsilon.
Oh, okay.
Epsilon is small, this is a value epsilon smaller than this. Yeah, I'll show you later on a little bit more on that. So let's go for the simple Batman profile. Can we compute this explicitly? Of course, I told you that in pieces where one of the density exists and the other one doesn't, I have a explicit formula. Also, when the two of them exist, I have another explicit formula, but they depend on the parameters, the masses, and so on. Everything is coupled. You have to find if you really have a solution or not. So you assume that the support of one is given by that interval, the support of the other one is given by that interval, the B is less than C, you give yourself the two masses, and I'm going to assume that the sum is continuous. Okay? So I assume that the rho plus eta is continuous, so at B, which is the point of that I see this jump, okay? So I'm going to assume that the sum of the densities is continuous. Then you can solve that. Well, believe me that this is somehow the parameters, B and C, or all the constraints that you have. You can solve and you can show that there is a unique Batman profile of that shape. So you have a unique B, C, M1, and M2. For a given M1 and M2, you have a unique B, C, such that such a profile is a solution. Okay, and here what you have is the computation of the explicit formula that I have versus some numerical simulation we did that leads to the steady state that is of that form. The surprise here is that we have a solution of a system with nonlinear diffusion, which has a jump at some point inside the support for the rho and at the boundary for eta. And you know a little bit about nonlinear diffusions, this is a surprise, because nonlinear diffusions typically they will be continuous and then they have some problem of regularity when they touch zero, but not inside their support. So this is the first surprise that you get. Let me show you that dynamically, because it's always fun to have some movie. So that is initial data that leads to that steady state. You could realize that the initial data was symmetric, because if it's not symmetric, you have more mass on one or the other, it will not lead to a steady state. I'll come back to that later. So then, but you see that the evolution, finally, it adapts really to the steady state that we were computing analytically. Good. Okay. Now I come back to the question of Mitchell here. So what was the difference between one of the picture and the other one? It was the value of epsilon, but because for epsilon smaller than certain value, you can prove that there is only one steady state with that property, which is a Batman type profile. But as soon as you are larger than epsilon 1, and between epsilon 1 and epsilon 2, at least two steady state coexist. And it depends on also a little bit of mass that you can put outside. So you have this kind of corner-like Batman profile. And in fact, one ceases to exist after epsilon 2, this one, and only this one remains after epsilon 2, but for a certain period of epsilons, they coincide. So this tells you already that the zoology here is quite complicated about the number of steady states and what are the possible stability properties of those, that I haven't talked about it yet. Good, let's come back to attractive repulsive. What happens if one of the species likes the other one but not vice versa? So love is only unidirectional. So what happens is that there is a segregation, total segregation in the system. So there is not intersection of the support, okay? And that's again is something quite interesting. So what you get for a steady state, you can have this kind of a steady state that I call adjacent because the supports are adjacent to each other. So somehow the red goes around the blue and doesn't allow the blue to move, but the blue doesn't like it, so it's really separated from the red, okay? And although they keep some distance to each other, okay? They're really segregated. That depends on the epsilon, again. Good, and again, you can compute that explicitly. And you have all those kinds of interesting state states. Let me put again emphasis on that one. Why? Because you have full segregation of the supports, and also you have this sharp boundary between the supports. So you have a jump at the boundary on the value of the density. Again, if you do rho plus eta, you can check that in that case, then it's fine. Again, rho plus eta is continuous. So there is a relation, of course, of the slopes there. Good. So, in fact, this is not only the complication that you can get in such a simple model, but you can have even many other steady states. Because I look for a steady state that were symmetric. You think about it till now. They were fully symmetric towards the center of mass, with respect to the center of mass. But you can look for steady states in which, let's say, one of the species, let's say the red, compared to the blue, is a bit shifted. And compensating with the different heights, you may have a steady states. You do have them. And this even, you have a range for how you can move this around. And also, apart from the steady states, yeah, the other thing I want to put a bit of emphasis, apart from steady states, you have traveling solutions, plenty of them. So essentially, as soon as you unbalance the mass that you put outside in the right way, you will make the pattern to move in one direction or to the other. Okay? And you can find them, again, explicitly. So you see, the interest about this model at the end of the day is that such a simple model contains lots of different interesting solutions and different features that leads to this kind of segregation of the two species. And here you have a kind of segregated traveling wave thing. Okay? Mathematically, to make sense about this is not so easy, as I will try to explain you in a sec. Okay. Good. Does I like to continue? Now, okay. So let's make it simpler. Let's avoid all the drifts. Let's start with just the two. Yeah. Well, I mean, I didn't say that. I put periodic boundary conditions here. So they will show up from the other side. Yeah. I didn't put boundary conditions to complicate my life. It's already complicated enough. Okay? So let's start without the drift. So what I said, I mean, let's put all the potentials to 0. So I have these two equations. As I said before, if I add them, I had Porus-Million equation with m equals to 2. We know everything about that equation, essentially now. Okay? We know the central behavior is given by something that is called the Barenblatt solution, which is a kind of inverted parabola cut it at 0, and that's the asymptotic behavior. But what happens if I look at it as a system with two in this way, and what happens to each of the two faces? We know what the sum is going to do, but do we know what is going to do each of them? So the issue is that this question is already there. So if you do that, this is what you get. Of course, at some point you see the Barenblatt. Okay? Why it goes to constant? Because here I have no flux boundary conditions. So then when the Barenblatt touches the boundary, then it becomes, it goes to uniformly constant. But what the issue that I want to emphasize is that you have this, again, this sharp interface between the two. The sum, we know what it does, but not each of them. So the question is, it's easy to get estimates for the gradient of rho plus eta, but it's very difficult to get estimates for gradient of rho or gradient of eta separately. This is what it's telling you already this. Well, it tells you that you have to find them in different spaces. More mathematically speaking, I would say maybe you expect that the gradient of rho plus eta is in H1. So you expect that you have good regularity for the sum. But for each of the two densities, you would expect only to have a bounded variation estimate. You will have something that controls the jumps, but not more than that. So how to get that? So the answer is the following. The answer is simple in the previous model that I showed you. The answer is simple because I don't know how to do it yet. I don't know how to do it in the case with potentials. Okay? And I'm going to try to convince you why it's hard. I already explained you why it's complicated, because you want to have estimate for each of them separately, but only you have it for the sum. And in the case in which I only have that kind of term that I showed you before, if you have a problem with the chi prime, put chi prime equals identity, and you have rho plus eta, but it can be done more general. Okay, so I can do it with more general nonlinear diffusions. But I can do it for the reaction diffusion system. If I have only the diffusion term, but I have reaction terms, and the reaction terms are not too complicated, and I'm assuming something nice about them, which some regularity and some hypothesis to keep the positivity of both rho and eta. So they are quite natural assumptions, in fact. So then we can do that, but I only know how to do it in one dimension. And again, the complication here is how to get estimates in BB for each of the two species separately. As soon as you have something that breaks the symmetry of the role of rho and eta, in the diffusion is fine. But if you had this diffusion that is so symmetric, that it only depends on the sum, which is in fact quite natural from the point of view of the modeling, I don't know how to do that. But in the case of, as I said, one-dimension reaction diffusion, we know how to do. And the trick here, it was to look at the system in different variables. So we define is the sum of the two, that we call it sigma, and we define the volume fraction of one of them, which is rho divided by rho plus eta. And in fact, in one dimension, if you write now the system in terms of R and sigma, the equations become quite nice. And that's the main trick there. I'm not going to show you the details. It's Friday, end of the term, so I don't want to really bother you. I want to have good evaluations. So then I tell you just a little bit about the result, how we got it. So we assume rho and eta, which are BB and L infinity. And I assume that the initial value for the volume fraction is a BB function. So this is an assumption because, of course, this is defined how? It's defined by that quotient whenever this is positive, and I assuming that it has a representation by a BB function. So that's an assumption I'm doing on the initial data. Anyhow, it's quite natural from the, it includes fully segregated initial data. Then what we can construct is a time-symmetric discretization by a splitting scheme between diffusion and reaction that keeps those properties. So in fact, the important thing is that we get BB bounds on the two densities. And the interesting thing is that we can keep full segregation. So if the initial data are fully segregated, then the construction, the solution that we construct will remain fully segregated for all times. They will not mix. There was a previous result of Birch, Hilhorst, and Mimura in the 80s about this problem, but they were assuming that they were mixing from the very beginning. So they were not able to deal with fully segregated initial data. So at least we understand where the difficulty lies. Of course, if you see about the simulation that I showed you before, or a new simulation now, this one is for reaction diffusion. So you will see that the mass is not conserved, it will increase in this case because of the reaction terms. But in terms of the, when they meet, you see, they have the same business, you have this sharp interface, they don't miss at all, they continue growing because of the reaction terms until they fill the whole thing. There is no flux boundary conditions here, that's why they go up, and that's at a given time. So, of course, this is a numerical simulation, so in the numerical simulation, you always see a little bit of intersection. This depends on how you put your discretization too, but that's not a big deal. Okay, in any case, what I want to say is that you see that it seems that the gradients are getting steeper and steeper in the evolution, even if the initial data, they were not there. So what the best you can expect is to have a BB bound on the gradient. I don't think you can get better than this. And this seems quite coherent also with the simulations with the drifts, for which we don't know yet how to get those BB bounds. So, first open problem, there are plenty. Okay, let me, probably before this, let me go now to, Let me show you some simulations for the, where I have it? Yeah, this one. Let me show you some simulations for the case of the green and the red experiment that I showed you at the beginning. These are simulations that Hideki Murakawa did for me with the Finite volume schemes. And let's concentrate only on the second line. Forget about the first row and the last row. I don't want to discuss that now. So just the second row is exactly the model I showed you. Here you have this interaction potential, and you have this kind of volume constraint. And these four simulations are just playing with the strength in which the two, the green and the red, they like each other. Okay? So you have typically kind of four types of behavior. This one is when you have some mixing, the red and the green, they like. They don't. You don't make a difference between the two in some sense. While in the second one, somehow one of them, I don't remember which of them, I think the green, somehow surrounds the red. Okay, so you have this kind of engulfment. Then if you change we're changing just one parameter continuously, okay? And then at some point there is some kind of partial engulfment, and then they are totally separated. So just by playing with the way in which they like each other, you can go from total mixing to total separation or partial separation. So you see that, somehow such a simple model, completely independent of any Turing business or anything, can lead you to the formation of very complicated patterns. So that's somehow the message there. Let me come back now to the presentation and tell you something about the pattern formation zebrafish. These are things that we are doing at the moment. So it's just reporting a little bit about ongoing work. So we started to discuss about this type of models with Shigeru Kondo in Osaka University. He's one of the groups that has been working quite a lot in this trying to explain this pattern formation. And so we tried this kind of modeling that I mentioned to you, in this particular case. So let me explain you the basic things that we include, according to Shigeru Kondo, that we included in the model. Okay, complicated enough. We try to include the basic things that he thinks are really somehow essential. So there are three types of cells that are essential. They are involved in the formation of the zebrafish pattern. The melanophores, the ones that gives you the dark color. The xanthophores, that gives you kind of the yellowish color. And the iridophores, that they don't give you some kind of color, but they are in the background and somehow interact with the others. So we apply that kind of model in terms of attraction repulsion between xanthophores and melanophores, while the iridophores are included in the model like a driving mechanism for the others to move. So we have some potentials for the interaction between the yellow and the black ones, and that I will show you in the next slide. So here is the system somehow. Sorry about, you don't see the yellow, it doesn't matter, it's the density of xanthophores. So you have the system of equation that I showed you before for the xanthophores and the melanophores with attractive repulsive interaction between the two, because according to the experiments, this is the xanthophores, they like the melanophores, they don't like the xanthophores, and then they have even movies in which you see the xanthophore chasing the melanophore. It's quite interesting. And then we included the repulsion by that kind of nonlinear diffusion term. And for the iridophores, right now we just included here, no, it's correct. We included some direction of interaction, either they like or not the xanthophores or the melanophores, the iridophores. But here we are working to improve a bit the modeling because one has to add also reaction diffusion terms to take into account cell and death. But nevertheless, just this very simple model, does it give you something that is coherent? Okay. So here you have the initial data we took, which you can think about this as one side of the fish. Okay, so that's the part where the fin, the dorsal fin and the ventral fin are, and this is the center. And according to them, the melanophores initially they are growing and going inside of the skin from those locations. So that's why the initial data of the melanophores is concentrated on these three locations. We are assuming periodicity over here and no flags on the top at the bottom. Okay, while the xanthophores they are initialized uniformly, and the iridophores also they say that at the beginning they are growing from the center, that they call the myoseptum. Okay, so this is the simulation. So the interesting thing about the model again is that it gives you, apart from that, it gives you kind of stripe patterns if you choose the parameters correctly. It gives you the formation of those stripe patterns really sharp. So you have sharp interfaces between yellow and black because precisely of the good choice of the nonlinear diffusion terms and things like that.
When you say choose the right parameters, so for the kernel, do you mean that there's arbitrary parameters on the kernel? Or?
No, I meant rather the diffusion, the diffusion parameter here. And related also to the strength of the different potentials. The shape of the potential, we fix it from the very beginning to something. Yeah, in this case, they are Morse-like potentials.
Right.
And we fixed the shape of the potential, and what we adjusted were the strengths of the different potentials for self-interaction or interaction between the two species, and the density and the diffusion. Okay, and you can get plenty of other patterns that are not stripe patterns too, and that they see also for the fish, by the way. The interesting thing, okay, you see here the diffusive part, the formation of, you here have both the black and the yellow, so the melanophores, the xanthophores, so you see that there is the intersection of the support essentially is just at the boundaries. So from that point of view, it's quite nice because if you will put other type of models, when you put just linear diffusion, then you don't get, of course, this kind of sharp interface. Let me mention that in this direction there is a work of Sandstede, Bjorn Sandstede and Alessandria Volkenin in Brown University that they did quite a study about the agent-based model behind this, just doing particle simulations. And essentially the particle simulations, they agree somehow with this kind of systems, because if you do the mean field limit over what they were doing in the agent-based simulation, you get to this kind of equations, in fact. So the interesting thing again about that equation is that, okay, so you get the formation of these patterns without any kind of Turing instability business behind. It's only based on the different strength of attraction and repulsion between the particles. Good. So, in fact, I think this is what I wanted today to report, more or less, because I wanted more to talk to you about things that I'm interested at the moment, and even if they are not completely finished and unrounded. But just here you have, let me do a list of the take-home message. You want to remember something. So first, one of the open problems that we have a well-Postness theory for system of these nonlinear diffusions with non-local drifts. This well-Postness theory is lacking. I mean, we don't know how to do that because we don't know how to get good BB bounds. In the sense, it's lacking in the sense that, I don't want a local well-Postness theory, that's easy. I want something that includes the steady states I had, that they had these sharp jumps, okay? I don't know how to get BB bounds. We know how to do that for the reaction diffusion system, but we don't know how to do it more than 2D. So, also it would be interesting to know if we can do something like that. And then the other thing that we are trying to continue is try to make the model for this fish patterning business more realistic and try to get some idea about the real parameters to fit to experiments. Okay, and let me just thank my collaborators. Most of the work has been done with my PhD student, Marcus Smichten, and a couple of the things are already sent to publication, and others are going to be sent very soon. And so apart from that, other collaborators that are listed there. Thank you very much.
Identical in both the species.
Yes.
And it's in the form of an epsilon times Dirac, say.
Yes.
But that's a parameter that does not need to be identical for both species.
Not necessarily, but that's why I said that, I think about it more as a kind of volume constraint. So, yeah, you could think that it's different, the volume constraint of the two cells, one is more, you could compress it more than the other, or things like that. You could do that. It will lead you to different strengths, both for the rho and for the eta. Do you have the same difficulties? I believe so. Let me see.
In that situation, perhaps a thing to look at would be some sort of scaling involving both the epsilons and the masses.
I haven't thought that much, but let me tell you one thing. As soon as you break the symmetry, you simplify things. Because that's what I said also before, that it's totally symmetric, it's worse. If you break the symmetry and you have a little bit of diffusion more on one than to the other, then you can get a priori estimate on that one. And then from there you have, because you have also the sum, you will have on both. But there is a catch there. Then you can show that at least in the steady state, when you compute the steady states, you will have things that intermingle, that they don't have sharp interfaces. You pay there. So it depends also from the modeling point of view what you want. You think that what you have to have is really sharp interfaces. I think it's better to have asymmetric repulsion. If you have asymmetric, you will have the state states will have some intersection, and they will be more regular. They will not have sharp fronts, at least with this type of model.
The reason this came to mind was because if you didn't have a symmetric situation, you as you said, you could analyze one as just a purely porous medium type of equation.
Yeah, more or less, yes.
And then as you let the relative strengths become similar, you could somehow try to examine the limit. So there might be some sort of a limit that would lead you to a BD type result. I don't know.
I know, I haven't thought from that point of view. I haven't tried to think in terms of, well, let's say the estimates I know how to do with the symmetry, they depend badly on the symmetry. If the symmetry goes to zero, then I don't get anything in the limit. But it's true that maybe there's another, I mean, there's something to explore there. If you can get estimates that are not using the asymmetry for the system and see how it works. Yeah, I fully agree. That's interesting.
Was continuity at the interface between the two densities, was that imposed on the system?
Repeat again, at the interface?
Was the continuity of the sum?
Yes, of the sum is imposed for the steady states. But nevertheless, for the theory, you can. It's very easy to compute an a priori estimate for the sum, because you see, you sum the two equations, you always get rho plus eta times the gradient of rho plus eta. So the gradient of rho plus eta square is good. So this tells you, in some sense, that rho plus eta is a continuous function in one dimension. So I impose it for finding the steady states, but somehow you expect it from the theory.
Mm-hmm. Also, when you're implementing this numerically, do you run into issues with this interface?
Well, we use a finite volume scheme. Then we are treating the system like a hyperbolic system of equations. So then it's good for these sharp interfaces, in fact. It's well adapted to that. But it's not simple, I agree. I didn't explain that.
So you explained in details about the population level, and you commented on the particle level. What about the kinetic level? Do you expect? Well,
I haven't thought that much about the kinetic level with two species. No, I haven't thought too much on this. And yeah, I mean, could it be useful for this story of the BB bounds? I don't know. I mean, it's something to explore. I mean, I put it there today more to say in general how I look at things. But in this particular case, I haven't thought yet. I mean, something to put it in the pipeline. Well, the thing, I mean, in general, as you see, you have a huge number of steady states. None of them is stable generically. Right. So, for instance, for the symmetric steady states, at least the Bandman profile in the interval in which is unique, then we expect to attract all symmetric initial data. Mm-hmm. And this comes from the simulations nicely. And also the traveling waves that we have, which is just about the difference of masses on one side and to the other, then we expect to attract initial data that are separated with that difference of masses. We don't know how to prove it, but this is what it comes from the simulations. But generically, finding, as you see, with the zoology of state states and traveling waves that you have, I think it's quite difficult to have a full answer of the stability. But particular questions like that, it could be interesting to find a good way to do that. Let me explain one thing here that I didn't say too much. They are not typically gradient flows. That's another thing that you have lost here. Only very particular cases are gradient flows. Only the cases in which W12 and W21 are equal, then they are gradient flows. So you are normally, in the cases I showed, you are not.
So all that machinery is gone.
It's totally gone.
Yeah.
So you have to deal with different ideas. You don't have typically Lyapunov functions that decay.
Right.
You will have functions that you get estimates, but not that they decay.